This is a video introducing you to distance time or displacement time graphs as used in Key Stage 3 and GCSE Physics. If you don't already know about speed, velocity and acceleration and how to calculate them, then I'd recommend starting with the describing motion video first. By the end of this video, you should be able to calculate speed based on a distance and a time, interpret dt graphs to describe the motion of an object, use the gradient of a dt graph to calculate speed, and use data to draw a dt graph of your own. To begin with, let's recap what we did last time, calculating speed using distance and time. The equation is speed is distance divided by time, and this is equation number 6 from the physics equation sheet. It's one of the ones that you need to memorise. So for each of the 5 calculations here, can you use that equation to write down what the average speed will be? So if a man runs 400 metres in 80 seconds, we do 400 divided by 80 to get a speed of 5 metres per second. If a car drives 300 metres in 10 seconds, 300 divided by 10 is 30, so the speed is 30 metres per second. 0.1 metres in 100 seconds is a speed of 0.001 metres per second. It's a very slow snail. The bird is flying at a speed of 6 metres per second, and the parachutist is falling at a speed of 50 metres per second. Now let's look at some dt graphs. They're called dt graphs because they represent distance or displacement on the y-axis and time on the x-axis. The AQA GCSE specification specifically refers to distance time graphs, but we will look at one example where we really need to use displacement. This graph is telling me a story about where a person or an object has travelled. It tells me that from 0 hours to 5 hours, where I've labelled it B, the person that this graph represents has travelled 3 kilometres away from their starting point. And then from 5 hours until 8 hours, they've remained 3 kilometres away from the starting point. It's taken them from 8 hours up until 12 hours to move until they're 12 kilometres away from the starting point, and then after 14 hours in total, they're still 12 kilometres away. By calculating the speed for each part of this graph, we can start to see what dt graphs are actually showing us. Now, in an exam, I would really recommend that you take a ruler and you divide up the graph into sections, because it's just going to make it much easier for you to interpret. To begin with, let's try to calculate the speed between point A and point B. As we've already said, this person has travelled 3 kilometres, and it's taken them 5 hours to do so. So to calculate the speed, we always do the distance divided by the time, 3 divided by 5, and that gives a speed of 0.6 kilometres per hour. If we now look at the graph between B and C, this person hasn't travelled any distance at all. They started out 3 kilometres away and they're still 3 kilometres away, so the distance is 0. 0 divided by 3 is still 0. So what this tells us is that wherever the graph is horizontal, wherever it's flat, that means that the person isn't moving, their speed is 0. So there's the first conclusion you can make about dt graphs. Anywhere that you see a horizontal line, this represents a stationary object. Now back to our graph. We're going to look at the line between point C and point D. It's important that we're only measuring the change in distance and the change in time, not the total distance and the total time. So I'm going to add some extra lines to help me. So for my change in difference, I want to know how far they've travelled if they've gone from being 3 kilometres away at point C to 12 kilometres away at point D. 12 take away 3 is a total change in distance of 9 kilometres. It's taken them from 8 hours up until 12 hours, so that's 4 hours. Now I can calculate the speed. 9 divided by 4 is 2.25 kilometres per hour. Looking at these numbers, you can see that the speed between point C and point D is faster than the speed between point A and point B, because it's a bigger number. 2.25 kilometres per hour is faster than 0.6 kilometres per hour. But what do you notice about the graph? The line between C and D is steeper. So what this tells us is that on a distance time graph, a steeper gradient or a steeper slope represents an object that's moving faster. So now we know 2 things about dt graphs. A horizontal line represents a stationary object and a steeper gradient represents a faster speed. Up until this point we've been making an assumption, but now we're going to say it explicitly. Here I have a graph that has a consistent gradient from A up to point C, and the halfway point is marked as point B. If I calculate the speed from A until B, then the change in distance is 3 kilometres and the change in time is 5. So that gives us a speed of 3 divided by 5, which is 0.6 kilometres per hour. If I then look at the trajectory from B until C, I've still got a difference in distance of 3 kilometres from 3 up to 6, and I've still got a difference in time of 5 hours from 5 up to 10. So my speed is still 0.6 kilometres per hour. What this tells me is that as long as my gradient remains consistent, the slope of the graph, then my speed also remains consistent. So now I know 3 things about DT graphs. A horizontal line represents a stationary object, a steeper gradient represents a faster speed, and as long as the gradient doesn't change, nor does the speed. If my object were accelerating, then rather than having a straight line with a constant gradient, I'd see a curved line like this. We can still calculate speed using a graph that curves, but what we have to do is take the start point and the end point and use those to calculate an average speed or a mean speed. You only need to be able to calculate the speed at a particular timestamp from a curved graph if you're doing the higher tier. This is one of the trickiest math skills in GCSE Science, but it's not so bad once you've had a practice and got the hang of it. Let's say that I wanted to know the exact speed at 15 seconds from this graph. The first thing that I need to do is draw a tangent, which is a long straight line that only touches the curve in one place. When you're doing this in the exam, I would really recommend that you either make sure you have a transparent ruler so that you can see the curve underneath it, or you put your ruler on top of the curve. You want to make sure that your tangent has gaps of the same size on both sides. You also want to make your tangent as long as you possibly can because this will make it more accurate. Once you've drawn this tangent, you can calculate the gradient of the tangent and it will be the same as the curve that it's touching. So here, for instance, the change in my y-axis, the change in distance, is going to be 1300 take away 400, which is a change of 900 metres. That time was from 0 to 25, so 25 seconds. 900 divided by 25 gives me a final speed of 36 metres per second. I mentioned earlier that AQA only lists distance time graphs in their specification, but there's one extra thing that we can show with a DT graph if we use displacement as our y-axis instead. Sometimes AQA do get around this by labelling the y-axis distance from home, which is just a less scary way of saying displacement. Remember, now that we're using displacement, which is a vector quantity and can be a negative number, we're technically calculating velocity, not speed. We're now going to look at the graph between points E and F, and we're going to calculate velocity because we're now working in terms of vectors rather than scalars, so we can have negative numbers. The first thing we need to do, just like we did before, is work out how far the object has moved, and we do this by taking the final displacement and subtracting the initial displacement. So here we've got 0 kilometres subtracting 12 kilometres, and so this time we get a negative number, which is why it has to be displacement, not distance. Distance being a scalar can only ever be positive. I take that negative number, that minus 12, and I divide it by the time. From 14 hours up to 20 hours is 6 hours. Minus 12 divided by 6 is minus 2 kilometres per hour. So what does that negative number tell me? It tells me that my object is moving back to its starting point. If we're looking at a displacement time graph, our first 3 points are basically identical, except now we're saying velocity rather than speed, because we're dealing with vectors, not scalars, and they can be negative. So a horizontal line still represents a stationary object with a velocity of 0, a steeper gradient represents a faster velocity, and a constant gradient represents a constant velocity. But the one extra point that we can say with a displacement time graph that we can't say with a distance time graph is that a downward sloping line represents moving in the opposite direction. Here are some quick questions just to check you've been listening. Pause the video and write down an answer to each one now. If a DT graph shows a horizontal line, that's because the object is stationary. If it has a constant gradient, that tells you that the object is moving at a constant speed. On this graph, we can see that the object is moved by a distance of 150 metres in 20 seconds, and so 150 divided by 20 gives us a speed of 7.5 metres per second. Rather than interpreting a DT graph, you could be asked to draw one yourself based on a story. Start with your axes. Time always goes on the x-axis at the bottom, and distance or displacement will always be on the y-axis. Next, you need to think about a sensible scale. You should always be aiming to use as much of the paper as possible for your actual data points. If we read through the story, we can see that this whole thing is going to take 35 minutes, and the furthest away they ever get from home is 1,000 metres. Based on that, this is the scale that I'm going to pick. Now I can read through the story and start to plot my points. I'm starting off from 0 minutes and 0 displacement. In the first section, Katie walks 200 metres to Pooja's house in 5 minutes. This is quite easy for me to plot because I'm just going to put a little cross at 200 and at 5 minutes and then join it up with a line. Pooja isn't ready, so Katie waits for 10 minutes. As we've already described, if an object is stationary, then we should have a horizontal line. So I'm going to have a horizontal line that lasts for 10 minutes from the point I'm already at. So it's not just going to go up to 10 minutes on the x-axis, it's going to go to 15. They then dawdle 200 metres from Pooja's house to Daisy's house in 10 minutes. So I'm going a further 200 metres away than I already am, so up to 400 metres, and it's taking me 10 minutes more than the point in the story I've got to, so up to 25 minutes. Katie then realises she forgot her physics book and rushes home in 5 minutes. To show that she's gone back to the starting point, we're going to go all the way down to the x-axis. And it's going to take another 5 minutes, so from 25 minutes, our line needs to go up to 30 minutes. Now they are late and they run 1,000 metres to school in 5 minutes. So we're going to go up to 1,000 metres displacement and the time is going to be 35. Thank you very much for watching, and I hope that was a useful introduction to DT graphs. If you did find it useful, then please like the video and don't forget to subscribe using the button below. There'll be more physics videos coming soon.